so like I mentioned in the first part of this paper, I was talking about how they discovered this cryptic pocket between these 3 amino acid residues, 95, 96, 99. And this is just them further trying to modify the compound they originally started with in order to make one that can be progressed into an actual drug. So like we said, where we left off, they were measuring the activity of this hybrid compound between ARS 1620 from the Nature paper in 2013 and indole-1, which was their original structure, so like what they first started with. And that was the one, if you remember, had like this weird cyclopropane attachment and just wasn't very good in the pharmacological properties, but it was a good inhibitor. And so they decided to make like this hybrid and see where they could go from there. So this is just a table from the first presentation I did, where it has the exchange IC50 and the p-ERK IC50, so the alpha screen and the immunoassay, which just again iterate how the exchange IC50 is how well that RAS coordinates with RAF. Obviously lower is better because you want them not to be able to interact with each other, so that disrupts the rest of the pathway. And then the p-ERK immunoassay is whether or not ERK, which is further down the line, is phosphorylated. So as you can see, this last compound down here has the lowest exchange IC50 and the lowest p-ERK IC50, so they chose to pursue it, which is compound 9, but only the R-atrope isomer. And this is probably a new word. It was for me. So what is an atrope isomer? They are rotamers, like amides, how we learned about with DEET, can be rotamers and they can be detected via NMR. And they result from hindered rotation about a single bond. So if you think about like a regular singly bonded compound, so maybe like butane, for example, it's constantly moving and adapting into different conformations, which is how we learned about Newman projections. So there was the eclipse conformation, there's gauche, and then there's staggered. And each one has a different like level of steric or torsional strain. However, with these groups, which are usually biphenyl compounds, so 2 benzene rings attached via a single bond, there's a lot more steric strain around them because they are so large. So that barrier to rotation, because you have to rotate an entire benzyl group, is so high that these isomers are actually separable, which is really interesting. So you can isolate a certain isomer. In this paper, they call them R and S, but the usual designation is M and P for minus or plus. But that's just another like terminology thing. You can actually separate individual isomers if their half-life exceeds 1,000 seconds. So this is really long for an isomer to stay in one conformation. It's about 16.7 minutes. So if an isomer is staying in one conformation for that amount of time, it's good that you can actually separate it, and that's unusual for usual isomers. And they're detectable via NMR if their half-life exceeds even 0.1 seconds, which is obviously a lot shorter. But this means that if you run this compound, if it has a half-life long enough through an NMR, you will get 2 peaks, indicating the 2 different atrope isomers. Which, if you remember from DJ's class, you can't tell the difference between 2 enantiomers in NMR. You have to use a chiral auxiliary, make them into 2 distinct diastereomers, and then you can actually separate them in NMR as 2 separate peaks. But since these have such a slow rotation, you can actually see them as 2 distinct points in an NMR spectra. And they can still interconvert and subsequently racemize, which we'll see as a problem later in the paper, but they do so slow enough that you can tell the difference and hopefully separate them. So this is just like an example of how this rotation and how the notation is for them being drawn. So obviously the larger these substituents are at the ortho position, so A or B or A prime and B prime, the slower that interconversion is. So if you think about A as like a tert-butyl group and B being maybe an isopropyl, the larger these groups are, the harder it is for these 2 compounds to adopt those different positions because you have more bulk to rotate around that single bond. And then if you ever see a compound drawn like this, where you have thicker bands within the ring, I think some of Lindsay's ligands actually had some of those thicker bonds, so those were atrope isomers. That just indicates that they have adopted a different conformation and they are atrope isomeric. So this will come back later, but originally they discovered that only the R atrope isomer of compound 9 actually worked. So they decided that maybe the stereochemistry is important in targeting this pocket. And so atrope isomerism comes back later when they further modify the rest of the compound. So this is their strategy. So from R9, which is this one, they decided to substitute this piperazine C2 position, which is R squared or R2 down here, in this wedged form, so in this certain stereochemistry. And that will allow additional contact with tyrosine 96 in the cryptic pocket. So later on, I have a picture of like how this actually bonds, but because of the orientation of this group right here, it pokes directly upwards into that 96 position and allows the pocket to be exposed even more. So this key C2 point in the piperazine ring is important in like opening that pocket and allowing for better binding for this compound that eventually bends upwards. And then replacing this fluorophenol group, which was R1. So there is a benzene ring with an alcohol down here and a fluorine up here. That's what R1 originally was. And so they're replacing that, which is on the very end of the molecule, which could increase both hydrophobic and polar interactions with the amino acids in the pocket. So since the fluorine and the alcohol were so near in like this interior part of the molecule, and then the rest was just carbon-hydrogen bonds, it can make contacts with both polar and non-polar amino acids and have increased basically just contact within the pocket. And then they also changed X basically to a nitrogen. So this was originally listed as A in the beginning, so they knew they wanted to change this position at some point, and this is the step in their modification when they finally started to switch it out with different atoms. So here is the first part of this very large table, and this is stuff that we've seen before. So the compound and its heteroisomeric configuration, R1, so that would be this group right here, that's what they're changing, R2 down here, and then X, which sometimes they left it just as a CH, and then towards the end they switched it out with a nitrogen. And if you notice, I included the p-ERK IC50, and what we're looking for is the smallest number. So how little can we get the ERK to be phosphorylated? How much can we disrupt this pathway? So right now it's looking like compound R11 is doing very well, 0.008, and then that's actually the best looking one out of these. The rest aren't that bad, but from just this data alone, R11 looks the best. Compound 10 actually didn't perform well for the remainder of the testing. I can't remember what they said was up with it, but I think it was due to the bulk of adding an additional like benzene ring up here. It just did not bind as well as they wanted to, so they didn't pursue adding anything larger than basically another fluorine at the top. So before we go into like the rest of the table, I think there's like another 7 columns. There are a few like pharmacokinetic terms that I learned. So I don't know how to pronounce this, so I'm going to call it the MIA-PACA2 cells. So they're just regular cells that have a KRAS G12C mutation. So they're kind of used as a baseline to see if these compounds actually target that particular mutant RAS. And then they're using A549 cells, which have a KRAS G12S mutation. So this will prove selectivity. If they target G12C more than they target G12S and inhibit its function more than this function, then you can prove that the compound is selective for this particular mutant only. So that's just good to cover that base. HepCl is drug clearance using liver cells. So this just means that since the liver kind of filters out toxins in your body, they're seeing how much of it can actually get past without being cleared out of your body or metabolized into different compounds. So a lower rate is better, means that a lower amount of it is actually like either metabolized into something else, broken down, or excreted later. MDCK is a measure of cell permeability. I think it's in microcentimeters per second, so it's a rate in these Madden-Darby canine kidney cells. So a higher rate means that it's moving further per second through the membrane. So membranes are that phospholipid bilayer with the polar heads and the nonpolar tails. So if these compounds can actually penetrate further through the membrane in a shorter amount of time, that's better because it actually needs to get into the cell before it can target RAS itself. And then they do a few solubility tests. So these are just what each individual solvent means. So PBS is a phosphate buffered solution. It's just buffered water. FASIF is a mock-up of gastrointestinal fluid. So this just means that since these compounds are administered orally, they have to be able to pass through your stomach acid and into your intestines in order to be digested and dispersed into your bloodstream. So obviously they have to be able to survive in that environment. And then HCl is just acidic water, which can also mimic other acidic parts of your body where these compounds have to travel. Cl is just another clearance rate, but this is in an actual mouse, like a whole organism instead of just liver cells. So once again, lower is better. VSS is the volume of distribution. I don't know why it's called VSS, but it's how well the drug is distributed in the body. So a higher number is better. And I wrote out here that that big number means the drug has moved into the tissue, which is what you want. It has moved from the bloodstream into the tissues and is able to target those cells that may have been infected with tumors. T1/2 we've seen in quant, it's just the half-life of the drug in plasma. Obviously longer is better because if it has a shorter half-life, that means you have to dose more frequently and it's not going to survive as long in your bloodstream and make it to maybe the infected parts of your body it needs to target. And then lastly is very important is this %F, which is the bioavailability. And that just means the percentage of the drug that actually reaches circulation in your body. So a higher number is better. So how much of the drug after you take it orally gets into your bloodstream and is available to do its job and make it into cells and target RAS. So you want a higher percentage of the drug to actually survive that journey into your bloodstream and subsequently into your tissues. So this is the remainder of this giant table. So we covered up to here with that p-ERK-IC50. This next column is the viability IC50 of the cells. So this MIA PAGA2 cells and the A549 cells. So these first ones are the G12C mutations, second are the G12S. So you want a lower number for the left side and a higher number for the right side. This indicates that the G12S mutations, the cells that contain these RAS mutations, are less likely to survive than the ones who don't have the mutation. If you have a low number on both sides, it indicates that the compound isn't as selective. It can target both, which isn't what you want. You want to selectively target only the ones that are mutated and actively causing cancer. So I've highlighted the compound they ultimately go with, which is R18, but you can go down the list and see that for the most part, most of these compounds do selectively target G12C mutations over G12S, with a few exceptions of higher numbers. There are lower numbers for the right side, so R11 has a lower viability for the A549 G12S mutations. That isn't ideal. Ultimately, you want it to be more selective on the left side and not target G12S, but obviously they chose to go with 18, which has 14.2, which is pretty high. This second column from that one in is the clearance in liver cells. So it's in microliters per minute per million cells. So how much of the compound gets through per minute per million cell. So we want a lower number, and we're focusing more on like the right side. I didn't ever figure out what mu meant in terms of clearance, but the HEP is just the liver cells, so you want a lower number, and R18 is at 38 when compared to some of the other ones like 197, 166, 317, that's performing pretty well. That MDCK permeability is in microcentimeters per second, so it's a rate of how fast and how far this compound can permeate through that phospholipid bilayer of the cell membrane. So this is where they begin to make some trade-offs in terms of the best compound. So compound 18 that they ended up going with isn't the best at permeability, but it does beat out other compounds in other columns down the line. So this is where they had to make some trade-offs in order to pick and choose which components of performance they wanted to see better of basically in a drug. So maybe permeability wasn't exactly something they're very focused on because R19 has 20 microcentimeters per second, 21 has 18. So this is where they began to like kind of pick and choose which components of this test they wanted to focus more on. This is just the solubility in PBS, the mock-up gastrointestinal fluid, and acidic water. So you want it high enough in all of them. So 0 obviously is not good because you don't want it to be insoluble in anything, but you don't want it to be so soluble that it won't come out of solution. So these numbers right here are acceptable. They're good that it can dissolve in PBS, it performs very well in the gastrointestinal fluid, and it can also be soluble in acidic water. So that's all well and good. And then lastly, they grouped together the mouse clearance, the volume of distribution at VSS, the half-life, and the percent bioavailability. So clearance, volume of distribution, half-life in hours, and the bioavailability. And from what I know, I think this is where they ultimately made the decision on which compound to pursue, because there's no contest with bioavailability for compound 18. 33% is by far the highest of all of these compounds, so I think that's why they chose to pursue it in the end, because more of it was able to survive your being digested and actually getting into the bloodstream, which is important for a drug because it has to kind of survive that pathway. So I think this was really the kicker as to why they chose to pursue compound 18. And then lastly, it has a half-life of about 1.3 hours, which does ultimately improve over time as they continue modifications.
And also, just for everybody to it's sort of obvious, but like how much work this table like represents, you know, in terms of synthetic chemistry, and then taking every compound and not only measuring how potent it is against the target, against the cells, and all these kinds of other things, but measuring all of these other things that are important for it to be successful in like to be used as a drug. It's like a lot, it's just an unbelievable thing. And sometimes there isn't like there's no one compound that is the winner at everything, right? So they have to make the best decision they can based on the number of compounds they're willing to make. Yeah.
They make a lot, so this is just a ton of time. But this is where atropisomerism comes back, and that's not good. So compound 18, they thought they had like a winner here. It had very high bioavailability, it was very potent, performed well in all of the assays. However, they realized that this compound itself in the R conformation only has a half-life of 8 days. So imagine you have like a bottle of this as a drug. If you don't take all of it within 8 days, it'll switch to a different conformation. But you might be thinking, like, why is this so bad? It's because that there's such a drastic difference in its potency based on which conformation that atropisomer is in. So if you have this isopropyl group kind of coming out at you, it has a PERC 2-hour IC50 at 0.004 micromolar and the PACA2 viability at 0.005 micromolar. So for both of these, lower is better. Less amount of the cells survive and less amount of ERK is phosphorylated, so that's good. It means the pathway is inhibited. If you look at S, the S conformation of 18, where that isopropyl group is going back further into the pocket of the cell, then the IC50 and the PACA2 viability increases by a pretty large margin. So not only is it actively racemizing, it's that this other conformation is not nearly as potent and is not nearly as helpful for being a drug. So what they did is that since they realized that choosing an atropisomer isn't going to be very easy at room temperature, you know, they have to run this risk of it actually racemizing, they used NMR. And so this is called a variable temperature NMR, or VT NMR. This spectra is of compound 27, which is just the one they chose to include. I guess the data looked the cleanest for this one. But as you can see, you have two distinct peaks for the atropisomers, because since their half-life is long enough, the NMR can tell the difference between the R conformation or the S conformation. I'm not entirely sure which is which. Then over time, as you heat these up and increase that energy that's available for these molecules to move around, so like we learned in quant, temperature is just a measure of like molecular motion. So as you increase temperature, the molecule is moving faster and faster and faster, which allows for more rotation. So as the temperature increases, these peaks like coalesce into one sharp peak, where the NMR ultimately can't tell the difference between the two atropisomers because they're moving so fast and have such a low half-life that it appears as one peak, much like enantiomers do. They just appear as one. So that coalescence point was about temperature 393 Kelvin, which is like 120 Celsius. That's pretty hot. And that's when these molecules actually can switch fast enough between the R and the S conformation that you can't tell the difference. So what they were trying to do with this equation up here This delta G double dagger is the interconversion barrier in kilocalories per mole. And what they're proving through this math is that it's temperature dependent. And since temperature is just a measure of energy, they're trying to figure out at what energy, like at what amount of energy we have to push into this molecule in order to get it to switch, in order to get it to flip or racemize into its other conformation. The higher, the better. So what they're saying is if this barrier is high enough, it won't actually switch at room temperature or body temperature. So that's what they're trying to do with this column down here, this interconversion barrier. So they started with R18, and they have it at 26.0 kilocalories per mole. And they set the threshold for like not good at 20 kilocalories per mole, and then good is over 30. So which, as you can see, like down here, they just put greater than 30. They didn't actually give like an exact number because 30 was that threshold that this will survive, this will work without interconverting. So they substituted different positions on that benzene substituent over here, which is labeled as R, trying to see if they could get that threshold to be above 30 kilocalories per mole, that interconversion barrier. And they did originally with compounds 23, R23, and R24, indicated by that thicker band. So they added a methyl group and kept the isopropyl, or just added a tert-butyl. And this is what was ultimately able to get that barrier high enough that they won't switch in and out of R and S. Then they switched down to 5-membered rings, maybe thinking that that would also prevent the barrier from being too low. It didn't work as well as they wanted to, but it was like a good learning opportunity as to see that maybe this conformation didn't work as well as they originally intended. And then the ultimate way to prevent A-trip isomerism is to prevent the formation of an A-trip isomer. So if you have a symmetrical compound, the R and the S conformations are the same because you have 2 methyls on either side. It doesn't matter which way it's rotated, it's going to be a methyl and a methyl. So they decided that if they make these molecules symmetrical, then there isn't an interconversion barrier because it doesn't matter which way it interconverts, it's still going to be the same functionality. And these, as far as their exchange IC50 and their p-ERG, weren't that bad. So originally they started out with just methyl groups, and they realized that that wasn't ideal because they needed that more kind of bulky substituent down at the bottom where the isopropyl usually is. So as they increased the size of these substituents, that potency increased as well. So you would think that they would go with compounds 31 through 33. However, they realized once again that 5-member rings were like worth a shot, but they didn't have a significant increase in the interconversion barrier. And then that symmetry is good because that interconversion barrier doesn't exist because of the same compound. So compounds 33 were the best at preventing rotation because it doesn't matter if you rotate it. But when they actually test these in terms of that larger table in the back for bioavailability and then all the other different pharmacokinetic properties, they had like low target coverage and extremely low bioavailability. So essentially, they just can't be drugs. They discovered a great way at preventing A-trope isomerism and a great way of finding a compound that would bind into that G12C, but it's just not good at being a drug. So they went back to R24, which was their most promising A-trope isomeric compound. So it can still interconvert, but it has a barrier that's high enough that they're willing to use it. So this is their exchange IC50 for the p-ERG, and then this was their viability for the MIA pocket 2 cells, so both very low. So they decided to pursue this substituent in the R conformation. And then they did more modifications. So there's their original group right here. And they're like, okay, we're going to switch up these 2 substituents and make them not carbons anymore. And then this was, I think, this was originally a chlorine, this R up here. And they're like, maybe if we change this, it'll do something. So this was round 4 of switching the original compound. And then so they did the same essential screening, so p-ERG, viability, clearance, permeability, solubility, and then clearance, volume of distribution, half-life, and bioavailability. So here are the changes they made. So they kept R as a chlorine for the majority and then switched it halfway through to fluorines, which actually proved to be very helpful. They kept X as either just a regular carbon-hydrogen bond, usually in a benzene, or they switched it to nitrogen, and they actually did that like off and on, off and on, off and on. And then the Y group did the same thing, keeping it either as regular CH or switching it to a nitrogen. So R38 is what they went with, which is why it's highlighted, where R is now fluorine up at the top, and X is a nitrogen, so this bottom part right here, they left Y alone as a regular carbon on the benzene. So what's interesting to me is the more trade-offs they made as far as like choosing the best compound, because this IC50 for p-ERK, like phospho-ERK, is actually higher for compound 38. And I thought that was kind of interesting how they chose to continue with this compound. As you can see, there's more promising data later down the line, but it allows more of the ERK to be phosphorylated, so it's not as potent as the previous compound that they started with was 24. And then the viability IC50 is comparable, 0.002 to 0.005. It's within that same realm. All of these compounds actually performed extremely well for the viability of the actual G12C mutant cells. And then the A549, which was G12S, once again, all of them performed extremely well with not targeting those cells as frequently. This one had greater than 50, which is pretty fantastic, but 36.5 is definitely greater than 11.9, which was their starting compound. And then clearance, once again, lower is better. So I think this was where they ultimately decided to switch downward. Since 102 and 30, I would choose 36 and 9 over that. Permeability in microcentimeters per second, 22 is pretty cool. Less than 1, not. So 6 is a good like happy medium for that. And then solubility, if you remember from the previous tables how low the original solubilities were for PBS and acidic water, I think it was 9 and 7 for compound 18. So over time, just making these little modifications drastically increase the solubility of the compound, which is very good. So a jump from 7 to 423 and 9 to 499 is commendable. And then the clearance rate, volume distribution, so lower is better for both of those. The half-life had decreased originally from 18, which I believe was 1.3 hours. Now it's down to about half an hour. But once again, that bioavailability is, I think, really where they chose to pursue this compound overall. They gave a range of 22 to 40%, which is higher than all of these other percentages for bioavailability. All of these were less than 0.5, so you don't want that. You want more of the compound to actually survive. So once again, I think this is what they made that decision based off of, is the bioavailability of the compound, because ultimately that's what dictates whether or not it can be a functional drug. So after all these modifications, on their 38th compound, they found the winner. And then they decided to test it in real life to make sure, like, does this actually work against tumors in an organism as a drug? So this is a very interesting type of graph. So over on the side, this axis on the left is the relative p-ERK percentage of control. So the black, which is like VEH, just means vehicle. So it's just like, it has no active compound in it. It's just the same amount that's being dosed, but nothing in it that's a drug. So that's just their control measure at, if you just give them essentially nothing active, then all of the p-ERK is going to be phosphorylated 100%. And then this is the dose of their compound 38 in milligrams per kilogram, so from 0.3 up to 100. And then on this axis on the right is they're comparing how much of the drug is in either the plasma or the tumor. So plasma is in red, and you can see the error bars. And then tumor is that blue circle. But what's important to note is that this is like an exponential scale right here. And this, on the other side, it isn't. So I was trying to make comparisons earlier that like didn't make any sense. But it's because of that like exponential scale that you can tell the drastic difference between how much concentration of the compound is in both these like entities, either the plasma or the tumor. So at 0.3 milligrams per kilogram, really like nothing's happening. This is at 2 hours in. I really do not understand why more than 100% of the phospho-ERK, of the ERK can be phosphorylated, but you can just chalk that up to the data. So at 1 milligram per kilogram, you're finally starting to see a small concentration of the drug in the plasma, meaning it survives after 2 hours and it's getting into the bloodstream. And then over time with, not over time, but like with a higher concentration, more of the drug is being present in that plasma, and then less of the ERK is being phosphorylated. So it's working. So here you can see how the concentration in the plasma is increased and that bar is dropped. But the key happens at around 10 milligrams per kilogram, where the relative amount of ERK that's phosphorylated actually drops by half, so from 80% down to about 40. And you see that first iteration of the drug being present in the tumor. This is why that drop-off happens. In order for ERK not to be phosphorylated, the drug actually has to make it into the tumor cells in order to interrupt that pathway. So you would expect to see a concentration of the drug in the tumor when ERK is not being phosphorylated. And then with these higher doses of 30 and 100, the concentration in the tumor and the concentration in the plasma start converging, which is good. It's indicating that you have some present unbound in the plasma that's able to move into the tissues and some that's already acting and working in the tumors. And then since they discovered that 10 milligrams per kilogram is kind of that like sweet spot for getting the drug into the tumor, they decided to use a single dose of that concentration and measure its efficacy over time. So this graph was all at that 2-hour time point, and this one shows its activity at 15, 30, 60, and 120 minutes, or 2 hours. So the same rule applies basically for this left axis and the bottom axis. So it goes with the bar graphs. So there's that original 100% of ERK is phosphorylated when you don't give them any compound. After 15 minutes, you already see some in the plasma, and you see a little tiny bit in the tumor, but nothing is really happening to ERK yet because it hasn't fully permeated into those tumor cells. And then more of it is leaving the plasma and entering the tumor at about 30 minutes. And then that ERK is being less and less phosphorylated over time. So here's that 2-hour mark that they measured over here. And these are actually comparable. So as you can see, 40% of ERK is phosphorylated at 2 hours in this graph. About 40% is phosphorylated in this graph. The reason that it looks so different is because of the scales on either side. These concentrations right here, as you can see, it goes like 0, 0.5, 1.0, and this is exponential. So this little symbol right here for like the plasma concentration, the tumor concentration, is actually where this would be. But it's just due to the different scaling of these axes that it looks so different. And then lastly, they just compared the percent modification of KRAS G12C to the amount of ERK that's phosphorylated. So I mentioned that percent modification was a tool used in the Nature paper. So that's how they determined like their best compound was how much of the RAS was actually inhibited, how much of like the RAS in the tube was actually inhibited by this compound. So nearly 100% modification, which is good. And as you would expect, the more that KRAS gets modified, the more of the compound that binds to it, the less that ERK will actually be able to be phosphorylated, indicating that it does disrupt that pathway. And then their last data point was just showing that tumor size does decrease at certain dosage levels. So tumor volume in cubic millimeters. So if you just add nothing but solvent, essentially no active compound, the tumor continues to grow because it's cancer. It's going to continue to get bigger until you do something to stop it. But even with a dosage of just 10 milligrams per kilogram, it easily flattens out. And these are the days after they gave the mice these cancerous cells, and then they administered this drug orally at the same time and saw its effect on the size of the cancer cells. So this is the regression rate of whether or not it actually functioned against the size of the tumor. And then once again, this was just comparing how much of the compound is unbound in the plasma. So how much is just like floating around in your bloodstream. And it's the hours past the dose. So they gave this baseline of the 2-hour p-ERK IC50, which is how much of the drug is needed to inhibit half of ERK being phosphorylated. So that's the kind of their baseline. And what you notice is immediately this 10 milligram per kilogram dose and the 30 milligram per kilogram dose drops beneath that line at about an hour for here and maybe 2 hours for 30. But that 100 milligram per kilogram dose does stay above the baseline until about 8 hours. This is just their initial starting of like a dosing curve of how they would actually administer this drug to a person. And then this is finally how the drug actually binds 2 KRAS. So this is R38, what they went with. So there's that isopropyl group, which acts like a fork and kind of pushes, I think it's histidine 95 upwards and causes that rotation. And then there's the covalent bond between the acrylamide and the cysteine, which happens kind of just behind in the pocket. Another interesting thing to note is this is that methyl group we were talking about earlier and how it kind of pokes upwards into tyrosine 96. Another interesting thing to note is the conformation this piperazine ring takes. It's called a twist boat, which I had never heard of. So that's why it kind of looks like a figure 8. So there's chairs, which is like, headrest and footrest, and they switch between each other. There are boats, which is like flat in the middle, and then both ends of the cyclohexane point upwards. And then in their infinite creativity, a twist boat is just a boat that is twisted. So that is why it looks kind of like a figure 8. And that's actually the conformation. It naturally adapts to fit into this pocket, and it works well because it allows this methyl group to poke upward and access the rest of this pocket. So that's just how the drug fits in, and it fits in very nicely. And then I made this on ChemDraw, and it took like an hour, but this is their progression from their initial hybrid structure, and each one they chose after initial rounds of modification, all the way up to R38, which was their final. So once again, these thick black bands represent those atrobisomers, the R conformation, and you can see the difference in what they chose to modify in each round. So Z, X, Y, and R were changed. A was changed to a nitrogen. This was substituted more. They added the methyl group. They added the methyl group here. And then they substituted that carbon with a nitrogen and changed this to a fluorine. And an interesting thing we discovered yesterday is that this compound is otherwise known as AMG 510. So that's what was in the title of the paper. And it's currently in stage 3 of clinical trials against non-small cell lung cancer. So this is actually like, could be a real drug. So I think that's really cool. But that's